The circumference of any circle is a little more than 3 times its diameter. In other words, the ratio of circumference to diameter is about 3.14, a fundamental constant of nature denoted by the Greek letter pi. The area of a circular disk is some number times the square of its radius. This factor A is another fundamental constant of nature. Surprise! It's the same number pi. To see why this is true, unwrap half the circumference for reference. Divide the disk into an even number of equal slices and rearrange them to form a sort of parallelogram with the same area as the disk. As we take more and more slices, making them thinner and thinner, the parallelogram becomes more and more like a rectangle, with base pi r and altitude r, and the area is pi r squared. Here's another method. Divide the disk into concentric rings. Unwrap them and pile them up like this. As we take more and more rings, the stack looks more and more like a right triangle, with base 2 pi r and altitude r. Its area, 1/2 base times altitude, is pi r squared. The decimal digits of pi have no regularly repeating patterns. One of the most practical uses of supercomputers is calculating 1 billion digits of pi, a truly transcendental experience. Pi shows up whenever circles do, in formulas for areas and volumes of solids of revolution. But it also shows up in some problems where there are no circles at all. For example, drop a needle on a floor whose boards are twice as wide as the needle length. The needle might land on a line or it might not. Drop lots of needles. The probability that a needle crosses a line is 1/pi. The next example comes from number theory. Put a yellow dot at each lattice point whose rectangular coordinates have no prime factor in common. Another way of saying this is, put a yellow dot at each lattice point that's visible from the origin. The dark dots are hidden behind the bright ones. The probability that a lattice point is visible from the origin is 6/pi squared. Pi has something to do with prime numbers.